Welcome to AP Calculus BC class. Today our notes are going to come from section 11.2 in your textbook, which is about multivariate calculus, calculus 3, because we are beyond the AP exam. The topic for today is 3D vectors. So let's jump right in and get started. For our first problem, it's going to give us an initial point for our vector of 0, 5, 1, and it's going to give us a terminal point of 4, 0, 3. And here are our directions. First, we have to find the component form of the vector v. Then we have to write the vector using standard unit vector notation. And then finally, we have to sketch the vector with its initial point at the origin. So, for part A, we are going to do terminal minus initial to get component form. And we write that inside of the chevron symbols. So, we're going to go terminal x-coordinate 4 minus initial x-coordinate 0, then terminal y-coordinate 0 minus initial y-coordinate 5, and finally terminal z-coordinate 3 minus initial z-coordinate 1. And so that's going to give us 4, -5, 2. There's our component form of the vector. So then for part B, writing the vector using standard unit vector notation, if you will remember, our vectors are, when you did them in pre-calculus, you used i's and j's for the x's and the y's, but we'll add k for the z. So it's going to be 4i minus 5j plus 2k, and that's in standard unit vector notation. Now, the last part is sketching the vector. So the way we're going to do that is we're going to have our vertical axis is z, our horizontal axis is y, and then in 3D coming out toward you, whoops, it would help if I scooted this up. Coming out toward you is x, okay? So this is a little bit different from the way we normally set up axes. And we're going to go, all right, we have 4 for x. So on the x-axis, I'm going to count out 1, 2, 3, 4. And then for y, we have -5. So I need my negative y-axis to go to the left in the opposite direction. And we're going to go 1, 2, 3, 4, 5. And then we have a +2 for z over, up 1 and 2. Now, the vector will start at the origin, and then it's going to end at the point 4, -5, 2, okay? So if you look, if you kind of make a little parallelogram here, let's see if I can do this kind of in a dashed format. The X and Y would meet right here. But because of Z, I have to go up 2 from there. So I'm going to count up 1, 2 to right here. That's going to be the terminal point of my unit vector. My vector initial point at the origin, and then coming out not to the terminal point, but to the component form of the vector. All right, so next we're going to scoot to number 2, and number 2 has similar starting information. We have an initial point of 1, -2, 4, and a terminal point of 2, 4, -2. And for part A, oop, my little setup collapsed. Here we go. So for part A, we are going to find the component form of the vector. So that matches what we did on example 1. Then for B, we are going to find the magnitude of the vector. And finally, for part C, we are going to find a unit vector, which I accidentally said a moment ago, and I said mistakenly, in the direction of V. So for part A, this is easy. We're going to do component form 2 minus 1, 4 minus -2, and -2 minus 4, which will give us 1, and then that's 4 plus 2, so 6, and then -6. Okay, part B. We need the formula for the magnitude of the vector. So the magnitude symbol are like double vertical bars on each side of the vector name. This notation means the magnitude of V, and it's going to equal the square root of V sub 1 squared plus V sub 2 squared plus V sub 3 squared, given in component form your vector with with pieces V sub 1, V sub 2, V sub 3, which is what we just found in part A. So for this vector, the magnitude would be equal to the square root of 1 squared plus 6 squared plus -6 quantity squared. So the magnitude of V is equal to 1 plus 36 plus 36. So the magnitude of vector V would equal the square root of 70. Ooh, that's an ugly 7. 73. There we go. All right. Now, part C, the unit vector is equal to V divided by the magnitude of V. So you can also think of that as 1 over the magnitude of V times the vector V. So for this problem, we just figured out the magnitude was the square root of 73. So we're going to go 1 over the square root of 73 times our component form of the vector 1, 6, negative 6. So this will equal, in component form, 1 over the square root of 73, comma 6 over the square root of 73, comma negative 6 over the square root of 73. And we do not need to rationalize the denominator on that. So we are done with example 2. Let's see, we're doing a total of 7 examples today. So let's move along to number 3. Number 3 says V is equal to 1, 2, negative 3. The initial point is negative 2, 1, 4. Find the terminal point. Okay. So what we've got to consider here is that the initial point, point 1, is negative 2, 1, 4. That's given in the problem. But the terminal point, P2, we do not know. There's an X, there's a Y, there's a Z, but we need to solve for each of those. And the component form is 1, 2, negative 3. So what we can do is we can write 3 equations. We know terminal minus initial equals component. So if I take my terminal x minus my initial x of negative 2, that should equal the component x, which is 1. And then if we take our terminal point y minus our initial point y, that should equal the component of 2. And then z minus 4 would equal negative 3. And now we solve for each of these. So x plus 2 equals 1. I'm going to subtract 2 on both sides, so x would equal negative 1. Here I add 1 to both sides, so y is equal to 3. And here I add 4 to both sides, so z is equal to positive 1. So this gives me a terminal point of negative 1, 3, 1. And that is done. All right, number 4 says find each scalar multiple of vector v. And they give us the vector v in component form is 2, negative 2, positive 1. And this is a 4-part problem. A, we're going to do negative v. B, we're going to do 2v. C, we're going to do 1/2 v. And D, we're going to do negative 3v. So for part A, negative v, we're just going to take each element of vector v, 2, negative 2, and 1, and multiply them by negative 1. So we'll have negative 2, positive 2, negative 1, and that's done. For part B, we're going to double each element of vector v, so that's going to be 4, negative 4, and 2. For C, we're going to multiply each element of vector v times 1/2. So we'll have 1, negative 1, 1/2. And finally, for part D, we're going to multiply each element of vector v times negative 3. So that's going to give us negative 6, 6, and 3. All right. Number 5. Find the vector z given u is equal to 1, 2, 3. V is equal to 2, 2, negative 1. W is equal to 4, 0, negative 4. And we have this equation given to us. 2u plus v minus w plus 3z equals 0. All right. So what do we do here? The first thing I want to do, since we're supposed to find vector z, is I want to isolate z in this equation. So all the other variables are moving to the right side of the equation, and they will change signs when they do that. So 3z will equal negative 2u minus v plus w. And now I'm going to divide everything by 3 or multiply everything times 1/3. So z is going to equal negative 2/3 u minus 1/3 v plus 1/3 w. So z, my vector z, is going to equal, we're going to take negative 2/3 of u. So I'm going to take this vector u and multiply each element times negative 2/3. So 1 times negative 2/3 is negative 2/3. 2 times negative 2/3 is negative 4/3. And 3 times negative 2/3 is negative 2. So there's my negative 2u. And I'm going to put plus, and now I'm going to take a negative 1/3 and multiply it times each element of vector v. So 2 times negative 1/3 is negative 2/3. 2 again times negative 1/3 is negative 2/3. And negative 1 times negative 1/3 is positive 1/3. And now the last part I'm going to add is 1/3 of w. So I'm going to take each element of w and multiply it by 1/3. So I'm going to have 4/3, comma, 0 times 1/3 is 0, and then negative 4/3. Okay? Now, to get vector z, I'm going to take each of the x elements, add them together. So negative 2/3 plus negative 2/3 plus 4/3, comma. Now I'm going to take each of the y elements and add them together. Negative 4/3 plus negative 2/3 plus 0. And now finally I'll take each z element and add it together. Negative 2 plus 1/3 plus negative 4/3. Okay, so z is equal to negative 2/3 plus negative 2/3 is negative 4/3, and positive 4/3 makes 0. Then I have negative 4/3 plus negative 2/3, which equals, plus 0, negative 6/3. And negative 6 divided by 3 is negative 2. And now here I have 1/3 plus negative 4/3, which is equal to negative 3/3. Negative 3 divided by 3 is 1. Negative 1, sorry. So negative 2 plus negative 1 will equal negative 3. There's my vector z. Woohoo! All right. The next part that we have of today's lesson is called Cylindrical Surfaces. Okay, so what we're going to be doing here is creating graphs in 3D of different equations that we are given. So let's start with an easy one. how about y equals x squared? Now y'all know what that graph looks like in two-dimensional algebra. It looks like a parabola, right? But we're going to do this in 3D. So I'm going to draw my x, y, and z axis. Y goes directly to the right. X comes out toward you. And z goes straight up. Okay? So if you were to graph this in two-dimensional algebra kind of graphing, where x and y meet at the origin would be the vertex, and then the graph would form a parabola symmetrical about the y-axis, opening upward toward the y-axis. This is a very rough sketch, okay? But I want you to notice for 3D, there's no restriction on z here. So that means for this parabola, z could be anything vertically, up or down. So the way we represent this, and it's certainly not a perfect image, but is we're going to take like the vertex and go up a certain amount, and then from maybe each of these arrows, try to go up the same amount, like that maybe. And we're going to draw it's sort of like a parallel parabola here. So what I have formed is what we call a cylindrical surface. This demonstrates, and I know it's sort of hard to see flat because this is a 3D type of image, but it's kind of like this is a ribbon that goes up, and truly it would go up indefinitely, but we have just kind of shown how it has some height to it. You could kind of think of it as like this front part is facing you, and the back part that's curling around is like the reverse side of that shape. Whoa! Sort of like that. Okay. Okay, interesting stuff here. Now how about the next one? X squared plus z squared equals 1. Well, if you look at the form of that equation, it kind of looks like x squared plus y squared equals 1, which is the equation for the unit circle, right? It's a circle centered at the origin with a radius of 1, basically, but this ties in x and z, and it has no restriction on y. So I'm going to draw the three-dimensional coordinate plane. It's not really a plane anymore, is it? It's like space. Okay, so here's y, here's x, and here's z. So my center is at the origin. My radius is 1, but it's 1 like along the x-axis, so let's say this is 1 unit, and 1 along the z-axis, so right here. So I'm making a circle here, but there's no restriction on y. So it could be more off to the side, like if I made another circle here, or if I made the negative y-axis and made another circle here. Okay, because y could go off any which way. So it's kind of like I've got a tube. Whoops, I missed this. These should all be the same height. I apologize, my art skills are lacking. So it's like an infinite number of circles that are parallel to this one going along the y-axis, because y could be anything. So that was an ugly cylindrical surface. If you look in your textbook, you've got some pretty pictures of some to look at, so they can draw better than me. Well, they used computers, but you could Google cylindrical surfaces and get some pretty neat looking images. I told you there was only 7 examples, and there really is, but I want to give you some food for thought on number 8. What would the graph of z equals the sine of x look like in 3 space? Which of course just means like 3D space. So think on that for a moment. You know what y equals the sine of x looks like. That's your sine curve that you learned about in pre-calculus. It kind of yo-yos up and down between 1 and -1. It intersects the origin, okay? But this is z equals the sine of x. So how would that one look? Can you imagine it? Like that little sine curve going up and down, bobbing back and forth along the xz plane, but then stretching out like a little bumpy ribbon infinitely along the y-axis because it has no restrictions on y. Interesting, huh? You're going to get to try to draw a few of these little cylindrical surfaces in your assignment today. So, good luck. I hope you have fun. It's kind of interesting, different, new, and have a wonderful day. Bye for now.